and this is joint work with Seo Kim. So I guess many of you, maybe most of you, are not familiar with the subject, not concordance. So I'm going to start with brief introduction on the subject. And more importantly, I found out that some of you look very tired, so I'm going to try to finish my talk earlier, a little bit earlier. So suppose we have two nuts. So K and J are nuts in three sphere. Then they are just smooth, simple closed curves. Then we can define many equivalence relations on the space of nuts, and one of them is called concordance. So let me give a definition. So we say K is concordant to J if there exists a properly embedded annulus inside S3 times unit interval. So this is annulus such that on the boundary it gives us the both nuts. So boundary is the union of K times 0 and minus J times 1. Here by minus J I mean the mirror image of J with reversed string orientation. So I mean, for instance, if you have just a trefoil with this string orientation, then by minus J I mean just take the mirror image. So you have a left-handed trefoil and just reverse the string orientation. And I can give you a schematic diagram here. So we have a S3 times 0, 1. And on the boundary we have 2, 3 spheres. And at the level 0 we have K. And at the level 1 we have minus J. Then these two nuts should co-bound a properly embedded annulus. So I mean, it cannot, it does not need to preserve the T level. Even this annulus can be knotted inside the full manifold. Because we have a surface inside the full manifold, we have to clarify what category, the category we are working on. I mean, there is a categorical complication in full manifold. I mean, so there is a smooth case and topological case, and today I'm going to work on topological concordance. That means this embedding is a so-called topologically, locally flat embedding. So this is a weaker condition compared to a smooth embedding. So if you are not familiar with this notion, then just think that we have a topologically embedded normal bundle of the surface inside this full manifold. Okay, so this turns out to be an equivalence relation. And I'm going to use this notation. So K to the J means K is concordant to J. And there is another equivalent condition for being concordant. So the theorem is that K is concordant to J if and only if the connected sum of K and minus J is slice. So by slice I mean, so K connected sum minus J bounds a certain two disk inside the oval. So for some, again, topologically, locally flatly embedded two disk E2 in the four-ball. The string scale is the boundary of the four-ball, just a standard four-ball. So inside the standard four-ball, there are certain two disks whose boundary is the connected sum of these two maps. So this is an equivalent condition. So from this theorem, you can find out that for studying knot concordance, or finding out which knots are sliced, that is very crucial. Okay. All right. So we have this concordance relation, and it turns out that this concordance is very interesting in a closed subject in the sense that it has a very nice structure. By a nice structure, I mean if you collect all equivalence classes, which are called concordance classes, so collect all knots and modify concordance relation, then under connect system operation, now we obtain an abelian group, which is called the knot concordance group. So this is a group. So what is the identity? Identity is the class of slice knots. Knots which bound topological local flat two disks in the four-ball. And for the class of K, its inverse is the class of minus K. Again, minus K means the mirror image of K with reversed string orientation. Okay. All right, so we have this knot concordance group, and so why do we study? Why are we interested in knot concordance? First of all, to me, at least to me, just knot concordance itself is a very interesting and just a fun subject, and of course it has deep relationships with other subjects in topology. For instance, so let me denote the zero surgery on the knot by n sub k. So n sub k is zero surgery on K in S3, then it turns out that if K is concordant J, then n sub K, by the way, this is a closed three-manifold, and this closed three-manifold is so-called homology covariant to n sub J, the zero surgery on the knot J. So what does that mean? So that means if you have zero surgeries n sub K and n sub J, then there exists certain four-manifold such that it's bound with the union of those two three-manifolds, and the included maps induce isomorphisms on the homology groups. So concordance is related to, in some sense, classifying four-manifolds after certain relation. And furthermore, concordance is also related to.
Why did you have to say zero surgery? Couldn't you just fix any?
I'm sorry?
Couldn't you just fix any type of Dane surgery?
Any type of Dane surgery, any coefficient you mean?
PQ surgery or something?
Oh, then you can think about a rational homology coefficient. So I mean, if you use zero surgery, then we are now in the world of homology coefficient, and if you want to use rational coefficients, then you have to think about rational homology coefficient. So,
okay, I thought it wouldn't change any homology, but okay.
any homology?
Never mind.
Okay, actually I don't understand your question, but this zero surgery, maybe you know this.
But wouldn't MK and MJ have the same
Homology.
homology?
Yeah, they are homology as sometimes as
Well,
two.
even if it wasn't, as long as you fixed what type of Dan surgery it was.
Yeah, this is Dan surgery with zero framing. So you pull back solid torus, tubular neighborhood of the knot, and we just pull it back by taking the identification such that the meridian is identified with the longitude and the longitude with meridian. So that is the zero framing Dan surgery in 3-minute float. So they are homology S1 times S2. So is it okay?
Yeah.
Okay. Also, because determining which knots are slice knots is important, and if you take the, okay, I was trying to finish my talk earlier, but so if you take the prime power characteristic cover of the slit sphere around the knot, then now you have a rational homologous sphere, and this problem is related to find out which rational homologous spheres become the boundary of rational homology for. So anyway, so this is a cool subject, and this is also related to four-dimensional topological surgery. So by a link is a union of several disjoint knots, and if you can find certain links which are not slice, then you can prove that four-dimensional topological surgery is not available in general. And Michael Friedman in the 80s, he used four-dimensional topological surgery for specific cases to prove four-dimensional topological Bloch conjecture. So this is related with some hominiform theories. Okay, so right. So let me mention this theorem by Friedman. So it turns out that that is slice if and only if there exists a certain hominiform such that its boundary is the zero surgery on the knot, and W is a homologous circle, and finally, when you classify manifolds, fundamental group is very important. So we have one more condition on the fundamental group. So pi 1 of W is normally generated by a meridian of the knot. So if we can find this hominiform, then you will not use slice knot. So let me give you just a sketch of the proof of this theorem. Just a sketch. So one direction is very easy. So because K is a slice, now you have a slice disk. So S3K is the boundary of 4M, certain two disk, and then for W, just you take the complement of tubular neighborhood of the two disk inside the oval. Then this W satisfies all the desired properties. And the other direction is much harder, much harder. Here we need a heavy machinery by Friedman. So by Friedman, okay, first, so for your W, attach two handle with attaching circle, the meridian. Of the knot. Then it turns out that this is a simply connected homology four-ball by homology four-ball, I mean a four-unifold which has the same homology groups with the standard four-ball. So everything is just trivial. So simply connect the homology four-ball with S3 as its boundary. Boundary is S3. Then now we can use the heavy machinery by Friedman, the four-dimensional surgery theory, which I don't know much about. And it tells us that this manifold, so V is just the standard four-ball. And furthermore, if you think of the core of this two tandem, then that gives you the desired slice disk. So this is just a brief introduction on the subject of knot concordance. And from now on, I'm going to tell you some known results about knot concordance. So the first result I'm going to talk about is the result of Lubin, which was found in the 60s. So Lubin, Jerry Lubin, in the 60s. So he constructed a surjective homomorphism from the knot concordance group to a certain abelian group, which is called algebraic knot concordance group. Algebraic concordance group. And then he classified this group. So it turns out that this is isomorphic to the direct sum of infinitely many copies of Z, Z4, and Z2. So Z, Z2, and Z4. And we say that knot is algebraically sliced if it is 0 in the algebraic concordance group. So what does it say? It says that the knot concordance group has a homomorphic image which is huge. So that means this group itself is also a huge group. So this was proved by Lubin in the 60s, and in the course of proving this theorem, he showed the following lemma. So this lemma is an interesting one. So again by Lubin. So suppose the Alexander polynomials of two knots are co-prime. So the greatest common divisor of Alexander polynomial is just 1. These Alexander polynomials are the elements in the lower polynomial ring, so we can, which is principal ideal domain, so we can compute the greatest common divisor. And if two Alexander polynomials are co-prime, mutually prime, then under the following minor condition, there is, so let me say this in this way. So if K constant minus A is algebraic slice, then so are K and J. So if the connected sum of those two knots is algebraically sliced, then those two knots are also algebraically sliced under the condition that they have co-prime Alexander polynomials. So in other words, if you think about the contrapositive, then what does that mean? That means if K or J is not algebraically sliced, then their connected sum is not algebraically sliced. By the way, because we have this surjective homomorphism, that means sliceness are algebraically sliced. Slice means it's a 0 in the not concordance group, and algebraic slice means it's a 0 in the algebraic concordance group. So sliceness are algebraically sliced because 0 is mapped to 0. So if one of these two knots is not algebraically sliced, then that means the connected sum is not algebraically sliced. And if it is not algebraically sliced, then it is not sliced either. Then that means they are not concordant to each other. So K is not concordant to J. So it turns out that under this condition and under this algebraic condition, now we have this topological result. They are not concordant to each other. So you can raise a natural question. So the question is, this question is the main theme of my talk. The question is, so suppose we have co-primers in the polynomials. And furthermore, suppose either of two knots is not just a slice. So this is a much weaker condition than being not algebraically sliced. So we are weakening the condition assumption, and I'm asking if K and J are not concordant to each other. So is K always not concordant to J? By the way, just this condition is a minor one, because if two knots are sliced, then they are sliced knots means they are just 0 in the concordance group, so they are concordant to each other. So that is just the question is backwards then. So this is a minor condition, and more important condition is this one. So we have co-prime Alexander polynomial, very simple algebraic condition, and I'm asking if this simple algebraic condition determines a big topological property. So it might sound too strong, because having co-prime polynomials, that is just a simple one. So maybe one might think that the answer for this question is maybe no. I mean there might be counterexamples. So there might be some examples with co-prime polynomials, but just they are concordant to each other. But it turns out that as of now we don't have that kind of example. That kind of example is unknown. And for the rest of the time, I'm going to show you some positive evidences. And before moving on, I need to make one remark. And the remark is that so the remark is that, so in smooth concordance case, you can just count examples. So I mean in smooth concordance, we have examples with co-prime polynomials, which are concordant to each other. The reason is that it's very easy. The reason is that there exist non-smoothly sliced knots with trivial Alexander polynomial. So using that, somehow we can cook up the desired examples. But that trick does not work in topological case because a knot with three values in the polynomial is topological slice by three-dimensional work again. So this is just these are big results which are found in the 80s by Friedman and Donaldson. So I'm not going into this topic too much, but anyway, you can find an answer in smooth concordance case very easily. So let me give some positive evidences for this question. So let's think about some concordance invariants for doing that. So there are a lot of concordance invariants, but mainly I'm going to talk about three invariants today. So the first one is Leibniz invariants. I mean, the invariants will be used to obtain this surjective homomorphism and to classify this algebraic concordance group. And in this case, we have this lemma, the starting point. So this is the first positive evidence. By the way, the point I'm going to make here is that the Leibniz invariant is, in some sense, abelian invariant. So I'm not going to give you the details of Leibniz invariance, but the idea is that using the infinitesimally cover of the knot complement or the infinitesimally cover of the zero surgery on knots. So when you have the zero surgery of the knot, then think of the fundamental group, and because this is homologous on times S2, its abelianization is just Z. So we have a natural homomorphism to Z. And when you have a representation, then you can think of the corresponding covering spaces. So in this case, infinitesimally covering spaces, and using those covers, Levin found those results. And because this target group is an abelian group, I'm saying that this is an abelian invariant. And second concordance invariant is, so this is a true story in the 1960s, and in 75, Casson and Gordon found Casson-Gordon invariants. Casson-Gordon invariants. So it's probably around 75. So this is a powerful concordance invariant which is still used in many cases, and the crucial difference between the Leibniz invariant and Casson-Gordon invariant is the level of covering spaces. So I mean their invariant is somewhat complicated, so I'm not giving the precise definition, but the idea is that they used certain character on first homology of K to the R-fold bracketly cover. Branched along the given knot to a certain cyclic group of prime power order. So here P and Q are prime. And then somehow they obtained an invariant which is associated to this character, which is an element in certain L group. So the Casson-Gordon invariant is, in some sense, that is a Machiavellian invariant. It's a little bit hard to find out that Kesselguden invariance and Machiavellian invariance in this form. But it turns out that there are some variations of Kesselguden invariance found by some other authors like Gilmer and Friedel and more. So one of the invariance variations is as follows. So when you have through surgery and pi 1, then we can find a certain representation which vectors through at least in the module. Semi-direct product Z, and the target group is unitary group. But these vectors through this Machiavellian group, and using this representation, Friedel and maybe I would have to mention the name like Lubin. Anyway, some people obtained eta invariant as concordance invariance using this kind of representation. And this H1, first homology group is an abelian group. So this is a semi-direct product of two abelian groups. So this is a Machiavellian group. So this is a Machiavellian invariant. So from the viewpoint of covering spaces, it's like we are looking at covering abelian covers of abelian covers. So second level of abelian covers. By the way, if you do not know the definition of Machiavellian, then for group G, so zeroth derived group is defined to be group itself, and the nth derived group is inductively defined as the commutator subgroup of n minus first derived group. And the Machiavellian invariant means that the second derived group of the target group is trivial. Or just simply you can think that a Machiavellian group means the semi-direct product of two abelian groups. So anyway, here we are looking at abelian covers of abelian covers. And for this Kesselguden invariance, and Saigo Kim, my collaborator, in 2005, obtained the following theorem. So again, we are assuming two knots have co-primaries and the polynomials. Then he showed that if K connected to minus J as vanishing Kesselguden invariance, I mean if Kesselguden invariance is 0 for this knot, then solve to both K and J. So again, this is another positive evidence for the question or conjecture. So again, think about the counterpositive. If either of the knots is, if either of these two knots does not have a vanishing Kesselguden invariance, then this connected sum does not have a vanishing Kesselguden invariance, then that means this is not sliced, so these two knots are not concordant to each other. So this is another positive evidence. And again, let me point out that Kesselguden invariants, they are powerful concordance invariants, and they are still being used in many cases. So this is the second concordance invariance, and the last concordance invariance I'm going to talk about, and they are they are Kaplan-Teichner's von Neumann row invariance. So the third one is Kaplan or Teichner's invariance, which are obtained around maybe 898. I need more space for the invariants, so let me move on to the next board and I will write some diagram here. So the idea is to extend Casson-Gordon type invariants. So again, we have the fundamental group of the zero surgery and the knot. And Levin's idea is to use the abelianization, so looking at infinite cover. So he used this representation. Let me denote it by gamma 0. And Kakurama Taikano, they defined certain groups, gamma n for each n. So the next one is gamma 1, and gamma 1 is defined to be the semi-direct product of certain k0 mod r0 and gamma 0. So this is getting complicated, and I'm going to talk about what k0 and i0 are a little bit more a few minutes later. So again, first of all, this is abelian, and this quotient group is an abelian group, so this is the semi-direct product of two abelian groups, so this is metabelian. And then they iterated this construction. So we have gamma 2, which is defined as whatever it is, whatever it means, k1 mod r1 direct product, semi-direct product, gamma 1, and more. So, what is Rn and Kn? So when you have gamma n, so they are inductively defined. Everything is inductively defined. So when you have gamma n, then we can think of the group ring Z gamma n, and we can think of the quotient field. Actually, this gamma n, in general, they are not abelian. So this group ring is a non-commutative ring, but still we can think of the non-commutative skew field, skew quotient field. So quotient field of C gamma n, and that is the definition of Kn. And between these two, somehow they defined a non-commutative principal ideal domain, Rn. So this is non-commutative PID. I'm not going to give you the precise definition of this, but anyway, so everything is just defined inductively, and they defined these target groups inductively, and then more importantly, so let me give you some list of properties of these target groups and representations. So first, gamma n is n-solvable. So that means n plus first derived subgroup of gamma n is 0. And they constructed these homomorphisms representations, Phi's, and each Pn is dependent upon the choice of Pn minus 1 and some element in the so-called higher order Alexander model. It's getting complicated, but anyway, so Pn is induced from Pn minus 1 and a choice of xn minus 1 which is an element in the first homology group of M sub K plus surgery with, now I'm using the coefficient group R n minus 1. So what's that mean? So this gamma n is kind of a highly solvable group. So for instance, gamma n, the nth derived group is non-trivial, but the n plus first derived group is trivial. So whenever we go up, now we are looking at higher and higher curving spaces. So we are getting more and more information. I mean, if you take the universe cover, then you can much information from it, but it's very hard to deal with the universe cover. So instead of that, we are taking a ton of iterated abelian covers. Just take the abelian cover first, and then take the next level of abelian cover, and take the abelian cover of the previous cover, and just keep going on. So they defined these target groups and they constructed these representations, but the problem is that we are studying not concordance, which involves 4 manifolds. If you are studying just 3 manifolds, this is okay. We have covers, and you can just take out information from these covers for the given 3 manifold. But concordance is kind of a relation related to 4 manifolds. So I mean, for instance, if K is slice and W is slice is the complement, then now the bigger problem is, maybe the most challenging part is to extending these representations to the slice disk complement. I mean, there is an inclusion-induced homomorphism from here and here, and to extract concordance invariance, somehow we need to use slice disk complements, and to do that, we need representations not on the 3 manifold, but on the slice disk complement. So the problem is, when, how can we determine these representations which are extendable to the slice disk complement? And that is the most challenging part, and they clarified it. So they determined which Vn extend to Vn bar, Hyman to gamma n. Okay. So now once you extend the representation to the slice disk complement, then now we can define the obstruction or invariance. So in case of the analysis last night, then they showed that so-called von Neumann row invariance of this closed 3 manifold associated to each Vn which extended to Vn bar, which is defined to be the L2 signature let me just skip this part. So there's a von Neumann row invariant which is analytically defined, and they showed that this von Neumann row invariant should be 0. So this is a somewhat complicated invariance, but it reflects certain classical invariance at each level. I mean, if you look at gamma 0, then there is Z, so somehow this is related to Lubin's invariant. And the next level, gamma 1, this is Machiavellian invariance, Machiavellian group, so this is somewhat related to Kesson-Gordon invariance. And now, by looking at gamma 2 and higher gamma n's, now you can find more behavior of non-concordance which cannot be found using Kesson-Gordon invariance and some previous known concordance invariance. So using this, they found nuts, non-slice nuts, with vanishing Kesson-Gordon invariance. So I would say this is the most powerful concordance invariant, but I could say maybe this is one of the most powerful concordance invariants as of now. So in regard of Kaplan tightness invariance, in 2008, Saibu Kim and myself obtained the following result. So again, suppose two nuts have co-prime Alexander polynomials. And suppose, and if K connected sum minus J has vanishing Kaplan-Teichner invariance associated to gamma 1, just gamma 1. So this is, we are at the Machiavellian level again, which is similar to Kesson-Gordon invariance. Then, so do K and J. So this is another positive evidence for the question or conjecture. And finally, quite recently, we could extend this theorem a little bit further. So the theorem is, so again, Saibu and myself. Actually, we haven't laid it, so we got this result a couple of years ago, but we haven't written up the manuscript yet, so I would say this is 2012. So anyway, and unfortunately in this case, we couldn't get the result, the desired result, using the same assumption for the higher order invariance by Kaplan and Teichner. So instead, we are putting a little bit stronger assumption. So the assumption is that, the assumption is a little bit technical, and I'm not going to give you the precise terminology. But anyway, so let me just write down first, and then I'm going to talk about it. So suppose K connected sum minus J has splitting self-annihilating submodules with respect to higher order blank speed Lincoln forms. And if now K connected sum minus J has vanishing Kaplan-Teichner invariance associated to gamma n for all gamma n, then so do K and J. So what does that mean? Having splitting self-analysis of modules with respect to higher order branch-field linking forms. And this is somewhat technical, and I'm going to give you just the definition of this terminology for the first level. So it turns out that, so remember that gamma 0 is z, and in this case, I0 is just rational coefficient Laurent polynomial ring. Then for this zero surgery with I0 twisted coefficients, this is just a classical analysis model. I mean the first homology of the infinite square cover with rational coefficients. This is the classical one. And on this homology group, we have so-called branch-field linking form. So that's that. So there it is. So it turns out that this module is a tangent R0 module. Tangent R0 module. So when you pick two homology classes here, because this is tangent module, there exists an element in R0 such that Rx is boundary of a certain two chain. Then the branch-field linking form of x and y is defined to be 1 over r times the intersection of these two chain and one chain y. So this is kind of an equivariant intersection. Then for this branch-field linking form, you can define the notion of being self-annihilating. So suppose we have a submodule of H1. Then we say that P is self-annihilating if P is equal to P perm, and P perm is defined to be the elements in H1 such that branch-field linking form of x and y is 0 for y in the given module P. So why am I suddenly using this notion? The reason is that it turns out that if we have cofine analytic polynomials, then for any self-annihilating form of P in H1 of M, K equidistant minus J with either coefficients, there exists PK in H1 of MK with the same coefficients, which are self-annihilating with respect to the branch-field linking forms of K and J respectively, such that P is the direct sum of PK and PJ. So actually, for the case of Castle-Gordon invariance and Kaplan-Typhon's invariance associated to gamma 1, in the previous two theorems, we needed this co-primeness of other polynomials. To get that, we have this direct sum decomposition. So, I'm generalizing that condition to the higher order cases. So this means that whenever you have a self-analysis module, for the higher order as the module of the classicism, then that can be decomposed as a direct sum of self-analysis modules of higher order as the modules for those two nets like this. Then, why am I not using so-called higher order as the polynomial? It turns out that gamma 1 and gamma 2, this step is critical in the sense that R0 is a commutative ring, but R1 and higher Rn's are non-commutative rings. And for modules over non-commutative rings, just many things change. For instance, for the classical case, this identity polynomial annihilates every element in this homology group. But that does not hold for higher order cases. So there are some technical difficulties to deal with higher order Alexander polynomials. So instead, just I'm using these self-analysis modules. And one more question is, so this is a stronger condition than having coprime Alexander polynomials. And the question is, if this condition is kind of vacuous, I mean, I'm not, someone might ask if this condition is equivalent to the condition having coprime Alexander polynomial, and the answer is unknown. The answer is unknown about it. And one more final remark is that, so this is another positive evidence for our original question, and still we're not getting the answer for the question. But this theorem is already powerful enough to produce some unique examples. For instance, in Konkuk Uni, they produced the first example of nuts with I deleted it. So Konkuk Uni used their invariants to produce the first example of non-sliced nuts with vanishing Cassel-Gordon invariance. That was a big thing. So, in other words, they showed that their nuts are not concordant to the unnut. By using this theorem, we can show that their nuts are, in fact, not concordant to any nut of genus 1. So, I can show further. So, in the sense, this theorem is already useful. So, I have just 1 minute left. So I think I stop here today. Thank you.